So we'll start today with a new chapter, which is equilibrium of a rigid body. We have already studied before equilibrium of a particle, and we said that for a particle, we just consider sum of forces equals 0 because all forces are passing by one point. However, when we consider a rigid body, forces can act at different points of the body. That's why we can say that to ensure equilibrium of a rigid body, we need to satisfy two conditions. Sum of forces equal to 0 and sum of moments, and you can select any point in space that you want. You should satisfy that sum of moments about any point in space. So for example, you can take O anywhere on the body or outside of the body. So sum of moments about O of these forces should be equal to 0. Of course, not only of these forces, if you have couples, if you have moment vectors, you need to consider them. So when you say sum of moment about O, this will include summation of moment of forces about O, and also possible couples, moment vectors acting on the body. So plus summation of couple moments should be equal to 0. Okay? So these are the conditions to satisfy equilibrium. Now, in 3D, this corresponds to three equations of forces, sum of x, sum of y, sum of z equals 0, and three equations of moments, sum mx, sum my, sum mz equal to 0. So an equilibrium problem in 3D, we can solve up to 6 unknowns with 6 equations. However, in 2D, it will be just 3 unknowns because in 2D, you have forces are in plane, let's say xy. So sum of forces in x should be 0. Sum of forces in y should be 0. Plus, when all forces are in xy plane, then of course rotation will be around z. So in this case, for sum of moment, we just have to write sum of moment about z equal to 0. So in case you have a 2D problem, you can just solve 3 equations with 3 unknowns.
دكتور
Yes?
what do we have للتست رح يتغير شيء؟
Until now ما تغير شيء للتست بس إذا كتير تعوقنا to go back to campus we might add additional chapters.
can I ask you what did we do like last time؟ أنا لأنه my Wi-Fi منا stable أبدا.
I uploaded all sessions at the end of the YouTube playlist. I did problems on previous chapter.
Okay.
And
Thank
you
you.
have everything posted on the YouTube playlist at the end. So if you want to watch them, you can.
Okay, deal. Merci.
Okay. Now, in order to be able to apply equilibrium conditions, first you need to draw a three-body diagram. A three-body diagram is the presentation of all forces acting on a body. Okay, so it's a drawing where we present all forces acting on the body. But to be able to solve equilibrium problem, we should be familiar with the main types of connections. What do we mean by this? Okay, you know that to ensure equilibrium, you need supports. Supports are, if you want, external reactions, okay, that will prevent motion of a certain structure. For example, if I consider, let's say, if I take a very simple example, I have a box on a surface. Okay, you have the action of the weight, and the surface will do on your box a normal reaction. This normal reaction is the reaction from the ground on the block, will keep it in equilibrium. So the normal reaction of the ground will be equal to the weight in a way to prevent it from moving downward. Okay, this is called a normal reaction from a surface that is smooth. Okay, What if now I have a rough surface? If you have a rough surface, in case you try to move your block horizontally, the rough surface can develop friction force. So the reactions of the surface of a rough surface will be divided into two components. Okay? We have several types of reactions. If we talk first about, let's say, the roller. What do we mean by a roller? It's like a wheel, if you want. This is why we present it by a circle. If you apply a horizontal force on your structure, you can move it, okay? But if you apply a force in the vertical direction, you cannot move your system. So because a roller will prevent motion in vertical direction, so no motion in vertical direction, this means that it will not develop any reaction in X. It will only develop a reaction in Y. So if you have a roller, when you see this symbol, or when you see the symbol of, let's say, like this, a certain structures with wheels, several wheels, it's the same thing. It's like a roller. So it will prevent motion vertically by developing a reaction in the vertical direction, but it will not do any action in the horizontal direction. So this is for the roller. Of course, if I put the roller like this, let's say you have the beam placed like this, and this is your roller. You always take the force perpendicular to contact. And if your roller is positioned in this way, it will act now perpendicular to contact, so it will act in the horizontal direction. So it will prevent, in this figure, it will prevent your structure from moving to the left by doing an action to the right. Okay. Now, what about the pin? If you have a pin, okay, if you put a pin here and you have a rod attached to it, a pin will not allow you to move horizontally, will not allow you to move vertically. If you have a pin, you can just do what? You can just rotate. So a pin cannot prevent rotation, but it can prevent motion in both X and Y. So whenever you see, they tell you have a pin connection, or you have this symbol, when you see this symbol like this, or like this, then you can say that the pin, let's say you have a pin called A will develop two external reactions. It will prevent motion in X, so it will develop a force AX, and it will prevent motion in Y, so it will create a reaction AY. So the pin can develop two force reactions. Now, a third type of supports, which is, if you want in 2D, it can do the maximum possible reaction is the fixity or fixed support. What do we mean by fixity or fixed support? So for example, if you weld a rod on a wall, it's welded to the wall, okay? This means that you cannot rotate it, you cannot displace it vertically, you cannot displace it horizontally, you cannot do anything. This means that your reaction here, this is called a fixity. A fixity will prevent any type of motion. It will prevent rotation and translation. So it will develop force reactions, Fx, Fy, and also will develop a couple moment.
Okay.
Now, yes?
Please repeat the first one.
Yes,
the roller. I didn't understand it.
the roller. Okay.
Yes, please.
Okay. Look, if you consider a small cart and it has wheels like this, okay? And you are putting it on the ground. If you put on it a force horizontally, it will move, yes or no?
Yes.
Yes.
So the roller can prevent motion in this direction, parallel to contact line.
No.
No, but if you put on it a force that is vertical downward, will the cart move down?
No.
No, why? Because at rollers, okay, you have a reaction force opposing downward motion. Okay? So whenever
Yes.
you
Thank
have
you.
a roller, it will develop a force perpendicular to the contact line that will prevent motion in this direction. Okay?
Okay.
Now, if you have a smooth surface, as we were discussing before, a smooth surface cannot develop friction. It can develop only a force perpendicular to the contact line. So here, for example, this is the contact line. So the smooth surface with no friction will exert a force perpendicular to contact line. When we say rough surface, or sometimes we say smooth surface with friction, which is equivalent to rough surface. Okay, a rough surface can develop friction force. So a rough surface can develop two external reactions, one in X, one in Y. And already we have seen rollers or bearings, and we have seen a pin or hinge. So all of these were already studied in the previous slide. So here you have a pin or hinge. You can put two external reactions, while for roller or bearings, you have only a reaction perpendicular to this contact line.
دكتور هلا عم نحكي هون ك 2D مش ك 3D.
Of course, now we started with 2D, then we'll move after to 3D cases. Okay? Now, other types of connections that we can have in 2 dimensions, we can have cables. Whenever you have a cable, we have seen together that the cable can only sustain tension. It cannot oppose compression, okay? That's why if I put a force on the body in a way to cause tension to the cable, by action reaction, the cable will develop a force opposing this action. So always, whenever you have a cable, the force of the cable on the object is from the object towards the cable, okay, along the direction of the cable. While if you have a link, a weightless link, the difference between a weightless link and a cable is that the link is rigid. So it can sustain both tension and compression. So if you put a force downward, you are compressing the link will develop by action reaction on you a force that is upward. So the link can sustain compression and can also sustain tension. So in this case, you can have F downward or upward. You can assume a direction. And according to your solution, if you get a positive result, the direction is right. If you get a negative result, the direction will be opposite. So if you assume your force is down, you assume the link in tension. If you get F positive, then your link is in tension. If you get F negative, then your link is in compression. But for the cable, it's impossible to have a cable in compression. You have only one possible choice for a cable. This is the difference between cable and weightless link. Now for the roller, okay, we have already seen what to do. For the rollers, we consider, so here you have your wheels. So they will prevent you from pushing downward. If you push down, the roller will act upward, okay? But the rollers cannot do anything if you apply an upward force, because if you apply an upward force, you will detach, the rollers will detach from the surface, okay? So you can only, in the case of roller, you will prevent motion in this direction by developing an opposite force. Now, we have already mentioned smooth contacting surface. It's like the roller. It can do a force perpendicular to contact. Now, What about a member pin connected to collar on smooth rod? So what will happen if you connect your pin to a collar on a smooth rod? The collar will allow motion in this direction. So because of the presence of the collar, you can move in this way. So in this case, for this connection, you just have a reaction along the perpendicular to contact. It's true that you have a pin here, so the pin would prevent motion like this, but because you connected the pin to a collar, and the collar will allow up and down motion like this, so this combination of pin and collar will only react along this direction. It will just oppose motion in this direction. Whenever we say reaction, you should see what I cannot do. This system allows me to move up and down, so it will not produce a reaction in this direction. This system will allow me to rotate my rod, so it will not develop any reaction moment on me. It will just develop a force that is perpendicular to the contact line. Okay? Now, if I consider a smooth pin or hinge for a pin, as we discussed, it will prevent translation in X and in Y. So it will develop two force reactions. Now, what if I have a member fixed connected to collar on smooth rod? What do I mean by this? You have a rod and it's welded to a collar. Welded means they form one part here. This is one part, okay? Ask yourself, what can I do? I can move up and down. So no reaction in this direction. Can I move downward like this? In this direction? No. So this rod will develop on me a reaction force perpendicular to the contact line. This is the contact line. Can I rotate my rod? Also, I cannot rotate because this is one welded piece. I don't have the flexibility of rotation. If I try to rotate, I might have rupture. So I cannot rotate this structure about this point. This means that this connection will develop a reaction moment to oppose any rotation. So in this case, where I have a member fixed connected to collar on smooth rod, I have two reactions, a force and a couple moment. And finally, if I have a fixity or fixed support,
دكتور
I cannot
بالبن
do
مع الكولر
anything. Sorry?
بالبن مع الكولر فيها تعمل روتيشن.
البن مع collar فيها تعمل rotation, yes. Because look, you have the collar and the rod is pin connected to it. And you have like a pin here. Can you rotate the rod about this point? Yes, because it's a pin. It's not welded. It's not one part. These two are not forming one part. But when you weld it on it, okay, then it's like they become one rigid body. Like you cannot rotate anymore the rod relative to the collar, okay? Now, for the fixed support, it's like we have seen before. I cannot do anything. The fixity will oppose any motion of translation or rotation. So the fixity should develop a couple moment and two force reactions. So these are the types of connections that we can face in 2D. Now, to study equilibrium in 2D, I need to write three equations. And we'll see together that I have a flexibility on selecting these equations. What do I mean by this? I can first say, I can use two force equations. So sum of x equals 0, sum of y equals 0. And I select any point on my figure and I do sum of moment about. But also, I have the freedom to replace a force equation by a moment equation. What do I mean with this? I can say, to have equilibrium, sum of moment about A should be 0. So I can write a first condition that sum of moment about A should be 0. I can also say that to have equilibrium, sum of moments about B also should be 0. So the second equation can be sum of moments about B equals to 0. And now I can say this applies also to C. So I can add sum of moments about C equals to 0. It's right. So I can say, or I solve this system of equations, or I can solve 3 moment equations, but only 3, not more than 3. And if you add now sum of moment about D equals 0, you cannot solve for a force unknown, because if you write a force equation, this equation will be a repetition of these, and it will be proportional or combination of these equations. So it will not give you any addition. Okay, so in 2D you can maximum write 3 equations, and you have the freedom to write them as 2 force equations and 1 moment. You can select any point on your figure and do sum of moments about. You can say I can use 1 force equation with 2 other moment equations. This is also possible. Or I can use 3 moment equations. In general, forces equations are easier than moment equations. That's why in majority of cases I use 2 force equation and 1 moment equation. But this doesn't mean that I cannot use 2 moment or 3 moment equations. Okay. Now, how to select the equations? I should select them in a reasonable way, and sometimes, okay? For example, if you look at this figure, what do you have as external reaction? You have a pin at A and you have a roller at B. Because of this, okay, you say a pin can develop a X and a Y. While at B, I have a roller. A roller can only develop a force perpendicular to the contact line. This is the contact line. So I have, this is BY. These are the reactions developed on my structure. I have 3 unknowns to solve for, AX, AY, and BY. Okay? You can say, for example, to calculate BY in one equation directly. Okay, from one equation. Which equation can I use? Which equation will only have By as unknown? Who can tell me? Of course, these forces
Sum
are
of moment
given.
A. Sum
Yes,
of moment A.
yes, very good. If I do sum of moments about AX and AY will not produce any moment. So I just have By times this distance, plus I add moment of these forces, I calculate them, I know all of my forces, equals 0. So the only unknown will be By. I can solve for By. So while if I write sum of y equals 0, I will have 2 unknowns. I have plus Ay plus By and minus y components, so minus these components here, equals to 0. So I will have 2 unknowns. So it's better to start with sum of moments about A to solve for By first. Then I use sum of y equals 0, because once I get By, I can solve directly for Ay. And to solve for Ax directly, I do sum of x equals 0, since along x, the only unknown is Ax. Now, another possibility is to say, if I do sum of moments about B, I can directly get Ay. Because Ax is passing by B, no moment about B. So if I do sum of moments about B, the only equation unknown will be Ay. So maybe you can say, from sum of moments about B, I get Ay. From sum of moments about A, I get Ay. So I have these 2 unknowns. And then I just write sum of x equals 0 to get Ax. This is also a possibility. Okay? Let us solve the following example to practice on this. We have the following structure subjected to these forces, and it's supported by, when you see triangular symbol, it's a pin. So we have Ax and Ay at A. And at B, you have a roller. So you just have By. And the question is to solve for reactions at A and B. So we need to write 3 equations to solve for these reactions. The first equation can just be, as we mentioned before, sum of x equals 0, because the only unknown in x is ax. If you look at your structure, you have plus ax, and you have these two forces in x, so plus 2 plus 2. So ax plus 4 equals to 0. So you can deduce that ax is minus 4. Why you got a negative result? Because you did a wrong assumption for ax. Ax should not be to the right, it should be to the left. It's fine. So you can just say, since I got a negative result, ax is in the opposite direction. You can keep in your figure ax like this, but now in the coming equations, when you replace ax, you replace by a negative value. Or if you want, you can put the actual direction, and then you can deal with ax in this direction, and then you put plus 4. Okay. Now, if you paid attention from the beginning that ax should be to the left, you can put it from the beginning to the left, and then in your equation, instead of putting plus here, you will put minus ax, and you will get ax is plus 4. Okay, so you can assume what you want at the beginning, and if you get a positive result, your assumption is right. If you get a negative result, your assumption is wrong. So this is for sum of forces about x. Now I will move to sum of y. If I write sum of forces in y equals 0, I have two unknowns. Okay, I have ay and I have by. So if I write sum of y equals to 0, I get that I don't have any force other than these two. So no forces having y component. I just have ay and by. So I can say that ay plus by equal to 0. So they should be opposite. So I deduce from sum of forces along y equal to 0, I deduce that ay is equal to minus by. Okay, and I need an additional equation. Now, I have several choices. If I do sum of moment about B, the only unknown will be ay. If I do sum of moments about A, the only unknown will be by. So both are right. You can do whatever you want, okay? Let us say they did here moment about A. Let us do moment about B, okay? So if you do sum of moments about B equal to 0, if you look at your figure, you say ax is passing by B, it cannot produce any moment about it. Now let me select a positive convention. If I take the clockwise as positive, ay is upward, okay? Ay is up. So if according to my assumption, so it's producing a clockwise moment about B. So I can say I should take plus ay times this distance, the perpendicular distance. The perpendicular distance is just 2 meters. So I have plus 2 times ay. Ax has no moment. I move now to this force. This force is producing a moment about B. To find this moment first, I extend the line of the force and I draw the perpendicular to get the perpendicular distance. So this is the line of my force. To get the moment about B, I do the perpendicular from B. This is the distance of interest. So I should multiply by a distance of 1.5. And according to the right-hand rule, or if I do like this with my hand, okay, I have rotation in clockwise direction. So plus plus 2 times 2. Plus 2, sorry, times a distance of 1.5. Now, if I move to my second force of 2 kilonewton here, also it's producing a clockwise moment, but now the distance, the perpendicular distance is larger. If I draw the perpendicular, I have this whole distance, which is 1.5 plus 1.5 equals to 3 meters. So plus 2 times 3 equals to 0. So I deduce from this equation that AY is minus, it's negative. This means that I select a wrong sense for AY. AY should not be up, it should be down. Okay, so AY is downward. Now, please pay attention for something. If you have already written the equation AY plus BY, you considered in this equation AY to be positive up, but actually it's downward. So now all you have to do is just, you can keep the equation as it is, but you replace AY by minus 4.5, okay? You replace AY by minus 4.5. In case you didn't write sum of Y yet, you can update AY on your figure. You say AY is downward now, okay? Downward equal to 4.5. So if you do this, then when you write the equation, you can directly put minus 4.5 plus BY equals to 0. So, which will give you exactly the same result, okay? So in case you have written your equation already, you replace AY by the algebraic value, by minus 4.5. If not, you can update AY on your figure, you put it down, and then you say, I consider, since upward direction is positive and my force is downward, I put minus the value of my force. So minus 4.5 plus BY equals to 0. So of course, at the end, you will get same BY, same result for BY. Okay, so BY is plus 4.5. In this way, I have solved for my 3 unknowns, AY, AX, and BY. Okay? Any question on this example? Let us move to another example. So in this figure, from the symbol here, you can know the type of reactions. This is the symbol of a fixity. A fixity can develop 3 reactions, 2 forces, or AX or AY, and 1 couple moment, MA. And you want to solve for the reactions at your fixity, okay? So you need to apply 3 equations with 3 unknowns. What are your unknowns? RAX, RAY, and the couple MA. So here, you can start with sum of x equals 0. Sum of x equals 0, you have only RAX, so you deduce that RAX is 0. Second equation, sum of y equals 0. You have only RAY and minus 2000 equal to 0. So you solve for RAY equals to 2000. Finally, you have to solve for your couple moment MA. To solve for your couple, you can select sum of moment about any point in the figure. Please remember, the moment is not like a force, it's a free vector. Yani, what do I mean by this? If I have a force passing by A and I do sum of moments about A, this force cannot produce any moment about A. But if I have a couple at A and I want to do sum of moment about A, I should include the couple because the couple is a free vector. I can put it at A, I can put it at C, at B, nothing will change, okay? For example, if I decide to take sum of moments about B instead of A, if I want to write sum of moment about B equal to 0, as I told you, you should divide your moments into 2 parts. You say sum of moment of forces. So I consider sum of moment of forces about B. Plus I should consider all possible couples. So plus summation of couple moments equals to 0. So if I look at my figure, okay, if I do sum of moments about B, what are the forces doing a moment about B? First, RAX is passing by B, no moment. For RAY, I have a moment about B. To get the moment of RAY about B, I consider the following. I say I have a distance, a perpendicular distance of 3. And if I consider the positive direction to be clockwise, this force is doing a clockwise moment. So I put plus RAY times 3. Now, I still have this force, the 2000 new lb force. So the 2000 lb force, if I do the right-hand rule, it's rotating about B in the clockwise direction. So plus 2000 times the distance to B. The perpendicular distance to B is 2 feet, so times 2. So I am done with the first part of my equation. I am done with moment of forces. I still need to consider couples. I have 2 couple moments here. I have MA and I have this couple here. Okay, so as I told you, I don't care for the location of the couples. Wherever are my couples, it doesn't matter, because if I displace them, nothing will change. Okay, so I need to consider MA and MB. But since MA is counterclockwise and the positive direction is clockwise, I put minus MA. And also, since this couple is counterclockwise and my positive direction is clockwise, I put minus 3000 equal to 0. Okay, so this equation will close my system of equations. I already have RAY from previous step I replace. The only unknown in my equation is MA. I can solve for MA. Okay, and since I got a positive result for MA, this means that I assumed a right direction. So MA is counterclockwise. If I get a negative result, this means that MA should be clockwise. Okay. Any question on this problem? Okay, I will open a new session to
دكتور، لان احنا لما نكون حاطين الاسامبشن على مثلا اخدينا لفوق مثلا، وبعدين طلع معي بالمقلوب، لازم ارجع اغير ولا خلاص بكفي انه طلعت معي نيجاتيف اقول لك انه هي لكن
فيك ما تغير شيء. You can keep your equations as they are, but when you replace AY, you replace by a negative value. Okay? But if you changed on your figure, and if you got AY negative and you change it in your figure, you put AY down. Okay? And now you want to write some FY equals 0, then you put minus AY. Minus AY minus 2000. And then you replace by positive value. But if you don't reverse it, you keep it up. But when you replace numerically, you replace by a negative result. Okay? This is the only difference.
Okay.
So I suggest to keep the assumption as it is, but when you replace numerically,